So let me briefly recall the definitions from last time. We introduced this notion of a perfectoid Tate ring R, and so that's a complete uniform Tate ring, and there exists a pseudo-uniformizer pi whose p's power still divides p in the power bounded elements, and such that Frobenius is an isomorphism between the power bounded elements mod pi and mod p's power of pi. And last time I was asking whether there is a more general notion of a perfectoid Huber ring, and I was mentioning that Gabba and Romero were thinking about this, and after the lecture I checked again, and they have a new version available, and so they actually do this. So and so they also show that these are sheafy. And to be honest, I couldn't. Well, I mean, they work in even more generality. Like in the Finite space for them is not associated to just a pair AA plus, but also there is some open subscheme of the spectrum of A. Okay, let's not do this. Okay. And so we had this notion of the tilt, and so that was the following. So if we have R plus, what's R perfectoid?
Would ZP double brackets T1 over p-adic be such a ring?
Yes. ZP is cyclotomic.
Cyclotomic, sorry.
Yeah. So their approach essentially is to reverse the discussion from last time. So first they define what a perfectoid ring over Fp is, which is not so hard. And then they say that general perfectoid rings should arise by taking the bit vectors of such a guy and then embodying out by an element which is somewhat primitive of degree 1.
So whatever I have to do to make this theorem we talked about last time.
Yeah. Okay. Okay. Right. And so then we had R flat, which I defined as a multiplicative monoid to be this inverse limit of R, and then endowed with a ring structure. This is perfectoid of characteristic P. And so I should say that this comes equipped with a map of flat to R, which I denoted F maps to F sharp. A projection to the zeros term. And you also have a plus subring, which you can define if you like as the inverse limit of R class. And then the first theorem was such that such perfectoid guys are sheafy. And so if you let X be the adic spectrum of RR plus, X flat be the adic spectrum of R flat plus, then the underlying topological spaces are homeomorphic. They have homeomorphism. X to X flat. Let's denote this map by X maps to X flat. where the map is defined in the following way. The evaluation of f at the point x flat is defined to be the evaluation of this element f sharp at x. And so moreover, for u and x rational, so this also prefers rational subsets. Meaning, subset is a rational subset in one if and only if it's rational in the other. So what I'm writing now is unambiguous. The structure sheaf evaluated on U is still perfectoid. The structure sheaf of the Hilbert space evaluated.
You don't have to. Oh yeah. That's sharp. That's all right.
Okay, and so I guess I didn't state this definition last time. I can do this now. So perfectoid space. P-adic space. And so then tilting extends to spaces. By someone in Phoenix applying this.
Does it matter whether you say unstatic space?
Well, I mean, because they are sheafy, it doesn't matter. So it's really an unstatic space. And maybe it's also just, well, I'm defining only the notion of an analytic perfectoid space, and you could define more general guys, like going back to this book of Gabber and Ramiro. What else did I want to say? I wanted to make this warning that if spar R plus is a perfectoid space, not clear. It is not clear that R is perfectoid. So it might be that you have some sheafy Hoover pair R plus, where this may be Etale, such that after rational covering, this OX of U on this space will be perfectoid, but maybe the R itself is not. Although I would hope that actually this implication is true, but I have no idea how to prove it. So if it R is of characteristic P, that's okay. So that's, for example, written down in this paper of Buzzard and Verberg-Noyes. But because it's much easier to check whether something is perfect. So, anyway, so the other theorem I explained last time was.
So is it not possible for an p-adic space or for something to be not sheafy but sort of only locally sheafy?
Yeah, so in that, if you allow non-sheafy things in here, then there are certainly counterexamples. But if you require that R plus is sheafy, then it might be true that you have this implication. So the counterexample to this other assertion is also in this paper. between pairs S plus, perfectoid. And triplets R plus and some ideal J, where R plus is perfectoid of characteristic P. And J in WR plus is primitive of degree 1. Okay. So before going on, let me actually say what's so nice about perfectoid spaces and why they are helping us in this. So recall that what I'm really trying to do is define this category of diamonds where one should be able to take some kind of self-product of the adic spectrum of QP. And why do perfectoid spaces help us? That's because of two properties. First of all, they're actually, although they a priori do not look like this, a very general notion. So any adic space of a QP is in some sense locally perfectoid. And what you have to allow is Pro-Etale localization.
So in this theorem, the S, P is invertible somehow in respect to P?
No. That should be general.
So it could be also characteristic P?
That could be also characteristic P, in which case, so if this was itself characteristic P, then this ideal J would just be the one generated by P. I will actually quite soon restrict this equivalence to things which live over QP, but anyway. There's Pro-Etale locally perfectoid. So let me just illustrate this in an example. I will probably prove this later in general. I mean, probably this assertion was first observed by Colmes actually, who introduces the sympathetic algebras, which are special, which are a special sort of perfectoid algebras, and then shows that you can cover anything by such guys.
Any adic space over QP is Pro-Etale locally perfectoid, that's what it says?
Yes. And so the more down-to-earth version of the statement is that if you A is some Banach algebra, Banach QP algebra, there exists a filtered system of finite Etale A algebras AI such that A infinity, which is defined as the completion of the direct limit of the AIs, that this is perfectoid. And I would have to say which topology I put in the direct limit, and it's the topology making the direct limit of the power-bounded elements open and bounded.
Do you mean analytic?
I mean, it lives over QP, so it has a topologically unipotent unit anyway.
But before you say any adic space.
Well, if it lives over QP, again, it's analytic.
What about non-reduced spaces? As the perfectoid guys are always reduced?
Well, I mean, under this completion, you're somehow killing the non-reduced part.
Yes. But then the morphism is still Pro-Etale?
It's still Pro-Etale in my sense, yes.
Okay.
Well, I mean, it's still good enough because, I mean, all these topological information like underlying topological space and Etale morphisms and so on, they are seen by the reduced part. And so, anyway. So say if X is the p-adic spectrum of some simple algebra over Kp, so maybe some kind of disk of radius 1, I mean some annulus, so this is the set of all X such that X like X 1. Then this is covered by X tilde X spectrum of Kp cyclotomic, and you join all p roots of T as well, and then take the corresponding power 1 elements here. So this is the inverse limit of finite Etale covers, which you could take to be Qp adjoin p to the nth root of unity and only extract the p to the nth root of T. Which is finite design characteristic 0 because T is a unit.
One question I've always had about this is what do you do with the whole disk and not just the circle?
You embed the disk inside the circle as a small disk around 1.
That's what you must do, huh?
Or you can cover the disk with 2 circles.
You can.
Yeah, but I mean, if you really want to find Etale things here, then
Yeah. I mean, it makes things around.
mm,
They're not
if what they're saying is that if you look at the set of all X of absolute value most 1, it can be covered as the ones which are absolute value equal to 1 and the ones where X minus 1 is absolute value 1. Oops, sorry. Okay.
Sorry, what did you say over there? What, direct limit of, or?
Hmm?
Sorry, can't read. Inverse limit.
Inverse limit of the x n's where you don't go all the way, but just adjoin p to the nth roots. So perfectoid algebras exist in abundance, and on the other hand, tilting has a very interesting interpretation. So if X is a perfectoid space, so the way to think about tilting is the following: that all topological information for example, the underlying topological space, and what I will talk about today is that also the Etale site can be, are stored in the tilde, or can be recovered from the tilde. On the other hand, you forget the structure morphism to ZP. And one can actually formalize that if you know the tilde and the structure morphism, then you can get back your perfectoid space. So in the sense, this tilde precisely forgets the structure morphism to ZP, which is in some more or less a reformulation of that. So,
how can you talk about the structural morphism without having X?
It's clever, but it can be done, and I will do it in the next lecture on diamonds. Okay, so the following can be made precise. which I will do in the next lecture, that if you look at perfectoid spaces over QP, and no, I actually want them over QP and not, which would correspond to taking QP algebras there. Perfectoid spaces of characteristic P. Let's call them X. Plus some kind of structure morphism, which is not clear how I should do it. X to, or something QP. And so, if you want to talk about an object that lives in two ways over QP, which is essentially what defining the self-product of QP is about, then you can do it on this side because it makes perfect sense to have several structure morphisms here to QP.
But do you think there's some kind of descent from the universal cover of QP?
Well, you will see it in the next lecture. So in other words, we can somehow strip off the structure morphism from the rest of the structure. So, well, what this lecture will be about is about this Etale side. So, X Etale. And that is the same as the Etale side of the tilde.
The SPA-Z piece isn't some sort of, doesn't have some universal mapping property somehow? Well, how many structure morphisms can there be from X to SPA?
Well, this can only have one, right?
Yeah.
But this guy, I didn't tell you what such a structure morphism is, but this can have several. I mean, it can't be a morphism in any usual sense because this is of characteristic P, this is of characteristic 0, so it can't be some usual thing. On this side, it will make sense to have several such structure morphisms. So let me do the case of perfectoid fields. So that's, let's call it theorem 1. So that's, the first such theorem was proved by Fontaine, Winter, and Berger. And then the version I'm stating, I think, is independently due to Etale, you, and myself. So let K be a perfectoid field with tilde K flat. Then, first of all, for any finite extension, this extension will still be perfectoid. And so this means we can apply tilting to it. And so this way we get a functor from the finite extensions of K to what turns out to be a finite extension of K flat. Oh, maps to R flat. So this is an equivalence. Which also preserves degrees.
And separability.
And
separability both ways.
And well, all extensions of a perfectoid field are separable. So either it's of characteristic 0 or it's of characteristic P where it's perfect. And so the upshot of this is that the absolute Galois groups of K and K flat are isomorphic. And I've had long discussions whether I'm allowed to put it canonically there or not. Well, I think I'm still allowed because, I mean, the Galois group itself is not a canonical object, but the isomorphism is canonical in the sense that if you pick an algebraic closure of K, you also get a canonical algebraic closure of K flat. And then if you make this consistent choice of algebraic closures, they are canonically isomorphic.
Galois groupoids.
And yeah, and there are many other ways to say that there's something canonical, like if you talk about Galois groupoids, or if you talk about the finite Etale side or whatever. I think I'm running out of yes, sure. Again, then there is a theorem which is very much related to this. It's called theorem 2, which in the simplest case is due to Tate, and then in full generality appears in the book of Gabor and Romero. In the first book, it says the following. K be a perfectoid field, and L over K a finite extension. Then some technical thing is true, and I won't define this, but so if you look at the extensions of rings of integers, then this is almost Etale, almost finite Etale. Let me just give an example. And this example was certainly dealt with by Tate already. So you say you get your field K by starting with something small like UP and then adjoining lots of, making such a tower as there essentially. And say I take the tower given by the p power of P. And then I take some finite extension of it, say the simplest one you could imagine. Take square root of P and say P is not 2, otherwise I'm not doing anything. And so let's actually write this as a direct limit of things. So that Kn be the thing here and Ln be Kn adjoin square root of P, which is also Qp adjoin 2 times P to the nth root of P. And so certainly in characteristic 0, this is a separable extension, but let's look at what happens on rings of integers. So if you write the ring of integers of Ln, then you get it from the ring of integers of Kn, which is just Zp adjoin a P to the nth root of P, by joining one more element, which is 2 times P to the nth root of P. And so the relation is that x squared is this P to the nth root of P. And so thus I can compute the discriminant of Ln over Kn. Please don't ask me whether it's discriminant or the different or whatever. So if I call this f of x, then I can compute the ideal generated by f and f prime. So the f prime gives me 2x, but 2 is invertible, so this gives me x, and then I can kill off the x squared, so it's the ideal generated by p to the 1 over p to the n. Or at least it's in there. And so I think this means that the this thing is 1 over p to the n. And the thing is that this goes to 0 as n goes to infinity. Meaning that there is less and less ramification along the special fiber.
It's like the order of the ideal. It's like the order of the ideal. It's not the evaluation of the ideal.
So let me write. If I write this, does this sound okay?
discriminant will be p to the power.
Yeah. And it's supposed
It's
to be
p
getting
to the
close
well,
to
but
the- close to
isn't
the-
there some numerical variant which has some name? I think plotting is called delta.
We
Which is
didn't
just
define what delta means.
yeah. So delta is this thing which comes out to be 1 over p to the n. By passing up a tower almost perfectoid limit. And this is actually some of the critical thing which allows you to do computations in p-adic theory. Well, you can also take the tau which is given by the cyclotomic extension, and then what Tate used this for is to compute the Galois cohomology of the absolute Galois group of QP acting on CP. And so first he showed that the result doesn't change if you replace the absolute the QP bar by just the cyclotomic extension, and then you can do an explicit computation there. What I want to explain is that theorem 2 actually implies theorem 1. Using lots of stuff that's in this book of Gabba and Romero. So how does this go? So we have the category of finite Etale K algebras, which is just finite products of finite extensions of K. And on the other hand, we have these finite Etale K flat algebras. And what we have to do is get an isomorphism between these, get an equivalence between these categories. And one way to do this is the following. So let me choose uniformizers pi and pi flat such that OK mod pi is the same thing as OK flat or pi flat. So as I explained, you can find such things. And so by this...
So the hard part is the social subjectivity of the functor. You've got a functor if they're 1 L flat.
No, I don't know part 1. I actually have a functor in the inverse direction because it's... Why do I have a functor in the inverse direction? Because it's easy to show that any finite extension in characteristic P is still perfectoid. You just have to show it's perfect. And you have the general statement that if you have a perfect ring and a finite Etale extension of it, then it's still perfect. And then you can apply inverse tilting. And so you get a functor in this direction, but then you still have to show that this gives you a finite extension, but that's probably also not so hard. But so the hard part is to show that so a priori there could be lots of stuff here which doesn't come from here actually. That's in some sense the hard part. And which this very much relates to the fact that a priori don't know that these are all perfectoid. So also the second theorem is very easy in characteristic P. I will give a similar argument in a second. Okay, so if we would just consider unramified extensions of a field, then these are the same as finite Etale extensions of the ring of integers. And what the theorem of Tate tells you that if you put almost everywhere, then this is still okay. Okay, almost algebras. And I don't want to define these notions, but there is such a category which, by the theorem 2, you get an equivalence here. On the other hand, you can reduce such an algebra mod P, mod this uniformizer pi. Almost algebras. So this upper A stands for almost. That's because finite Etale algebras live uniquely over nilpotents. But now this is literally the same thing as almost finite Etale. Almost finite Etale. Okay, flat. Or pi flat. Almost algebras. And now you can just reverse all arrows and do the lifting non-characteristic p. Almost finite Etale. Okay, flat, almost algebras. And then use theorem 2 and characteristic p. Okay. And yeah. Yes. I mean, so that was actually how perfectoid spaces came about for me. So I realized that one could prove this kind of Fontaine-Witten-Berger theorem in this way, and that got me started. So my original proof of the equivalence of categories between perfectoid K algebras and perfectoid K flat algebras was along the very same lines. So some of the slogan is that for perfectoid things, everything that's true on the generic fiber somehow almost extends to the integral level, and then if it's almost on the integral level, you can actually model out P and still have information.
Are you going to define an OK almost algebra?
I'm defining an almost module at least. So for the course, I think we actually need very little of the techniques of almost mathematics. So we need to know when something is almost zero or so, but I will just define that. Almost mathematics. So this term was coined by Faltings, who wanted to have a general machinery available for discussing such statements, especially the theorem of Tate there. So let me work in the generality I'm in. So let me use as a base a perfectoid Tate ring. And I define that a module over power bounded elements is almost zero.
So, one question about this. So, when you identify these residues, the OK mod pi and OK flat mod pi.
Flat, yes.
I mean, I see you have to do it from the construction, but you have sort of a way to say. I mean, you could choose other isomorphisms.
Well, no, but there's one which comes out of the construction, which is given by the map F maps to F sharp.
Yeah, there's one from the construction.
But I use that one.
Okay, you just choose it.
I mean, what I mean choose? I mean, the tilt somehow comes with such a.
Okay, all right. It's part of the structure of the tilt.
Yeah. It's almost zero if pi times m is zero for all pseudo-uniformizers. Pi. And the equivalent way of saying this is that pi to the 1. Well, let's see what this is. So if let's do this. So it's equivalent to saying that pi to the 1 over p to the n m is 0 for all n. If pi is a pseudo-uniformizer with chosen roots of chosen p-power roots. And such a guy always exists. So I mean, these are all pseudo-uniformizers, so this certainly implies this. On the other hand, any pseudo-uniformizer is divisible by this for a big enough n. And one could make a similar definition for R plus modules, which is probably even more general. Maybe I should have done this from the start. So, in case of a perfectoid field, then you can look at the ring of integers and divide by the maximal ideal. And this is almost 0. And over fields, that's pretty much what an almost 0 module looks like. So if it's almost 0, it's a vector space over the sky, which is the residual field. And so, general 0 module. Darts or such. And you for as perfectoid and R plus and R zero is any ring of integers. Integral elements, I called it. Then the quotient of R naught by R plus, this is also almost 0. So as regards almost stuff, there's no difference between these guys. Why is that? So for
Did you take 0?
Any ring of integral elements has to contain an open and integrally closed. And so this actually implies fine. So for all pi pseudo-uniformizer and x the power bounded elements, pi times x will be topologically nilpotent. So the powers of pi will go to 0 and the powers of x will stay bounded. And so this means that there exists some n such that pi times x to the n is an R plus, because R plus is open. And because integrally closed implies that pi times x is an R plus. And so certainly if you have an almost 0 module, then any sub-quotient is almost 0, but also extensions of almost 0 modules are almost 0. For this, you should probably use this characterization. So, if you have an extension of two things killed by p to the nth root of pi, then the extension will kill by p to the n minus 1th root of pi. But if you do this for all n, then it's again the same thing. And so this means that almost 0 modules form what's called a sig Serre subcategory or something like this. And so you can take a quotient by it. So I define R steric almost modules as And let's write this out, almost R circle modules. It's the category of R modules, R not modules. Mod almost 0 modules. And you can do the same for R plus A modules. And then actually those two notions are the same, so R plus A modules. There's certainly a functor, and that's an equivalence. Essentially because these two rings differ by something almost 0. And so, well, I mean, one functor is tensoring and the other functor is for getting part of the structure, but maybe this functor is more obvious. Yeah. So let this be a perfectoid. Let's take it up here. X-adic spectrum. Then I recall that this is Schiffi, and by a theorem of Etale and Liu, we know that this implies that the cohomology of the structure sheaf is actually 0 for I bigger than 0. So that's some statement that's true on the generic fiber, but in this very same spirit, this statement actually is almost true on the integral level. So then, if I look at the cohomology of this sheaf OX plus, this is almost 0. Okay. Let's prove this.
And H0 is almost
and yeah, and H0 OX plus. Well, that's actually something we already know, that this is R plus. So it embeds into H naught here, which is R, and so has to be the correct. So in general, for a Schiffi ring, if we take sections of those sections of OX plus, we get back this. So to show that sheaf cohomology vanishes, one thing you can do is show that Čech cohomology vanishes for covering square rationals. So for any rational covering X is the union of some UI. And by quasi-compacity, you can assume it's finite. I'm not sure I'm using this, but anyway. All cohomology groups of the following complex, I'm going to call star, are almost 0. So 0 to R plus to the product for x plus of ui to product x plus of ui cap uj and so over 0. Okay. So what do we know? We know that if we take star.
So just, this is not immediately obvious. One has to use some spectral sequence argument. And
Yeah.
Reduction and so on.
Yeah. But I mean, it's a general lemma about sheaves on its side, which you probably have to check that everything works with almost instead of 0. But yeah, that's okay. Well, I guess almost modules still fall in the Being category. So if we know that if it takes a sequence and invert the substituting from other pi, then we get a sequence where we erase all the pluses. So yes. Is exact. So by some of the converse of what I was using here, that's equivalent to this vanishing of the comodules for x. I mean, not just for x itself, but probably also for all rational subsets at the same time. Okay. And before I start the proof, I should have said one can reduce to the case that R squared is the P. Case PR is equal to 0. By tilting. And I don't want to explain this reduction, which is not so hard. Okay. So we'll use this in a moment. So first let's use Banach's open mapping theorem. So this implies that so if we take the kernel of this map, it's some Banach space, and this map maps surjectively onto it, and so the map is open. But then we have natural open and bounded subrings on both sides given by these plus structures here. And so that it's open means that those two integral structures differ only by bounded pi power. And so one way to say what this implies is that if you look at the all cohomology groups, or I should say each cohomology group, star is killed by a power of pi. So a priori we know that each cohomology group is pi torsion, but it could be like some very big pi torsion in there. But Banach's open mapping theorem tells you that actually it's bounded pi torsion. But on the other hand, we have a Frobenius map which acts on all these things simultaneously, compatibly with all transition maps. And so Frobenius acts as an isomorphism or of star And so this means it induces isomorphisms of all cohomology groups. So this means that if they're killed by some pi to the n, then also by all pi to the n over p to the k. But this is exactly saying that they're almost zero. And so that's an argument which underlies, essentially also proves that something is almost true in this perfectoid setting. So you reduce to the characteristic p case. There you know that it's true in the generic fiber, so invoking some finiteness argument, it's true up to some bounded pi torsion, but then you can use Frobenius to make this pi torsion arbitrarily small.
Can you glue almost zero modules? So if you have almost zero modules over some cover,
I don't know, and I don't think so. The question was one can do almost modules. So if you have a, yeah, it can even. I mean, so there's the theorem of Kedlai and Liu that you can glue vector bundles over rho x. But there is a version of a vector bundle in this almost setting, but it's probably appealing to their result. You can glue them, but I don't. Yeah. It's not so clear. All right. And so I was promising to say something about the Etale side, so let's do this. So the key theorem in this setup is the so-called almost purity theorem, originally formulated by Faltings. Then some version of the theorem of the theorems I stated before is true. So, and actually the first two parts are also proved by Kedlai and Liu. So for any finite Etale R algebra S, S is still perfectoid. Secondly, tilting induces an equivalence between finite Etale R algebras, finite Etale flat algebras. No, S flat. And what's actually the almost purity theorem? And that's the analog is the theorem of Tate in this setup. That for any finite Etale R algebra S, if you look at power bounded elements, and this is still almost finite Etale over the power bonded elements of our circle. And I'm not defining what this means, but and a statement which is actually very related to this, and which is the one we will actually use, is that there exists an Etale side, X Etale. Oh. Well, no, let me say this later.
So every finite flat algebra over a complete uniform Tate ring is a complete uniform Tate ring.
Yes.
Yeah.
Yes.
What? No, not uniform. It wouldn't be uniform. I mean, it could be non-reduced.
Could be no. If you have a complete uniform, then it's not. I
mean,
think
if
it's
you
still
have a finite
uniform with
flat
finite
over that,
Etale.
you could just take a, you could just add a nilpotent, no?
Finite Etale, he said.
Well, he said
Oh,
flat.
you said
He's
flat?
asking flat.
Ah, no, then you could be non-reduced, yes. I was answering, so if you have a finite Etale algebra over a complete uniform ring, it's still complete uniform. If it's just finite flat, it's still complete. I mean, by finite flat, I read as finitely presented flat.
Yeah.
Yeah. Then it's still complete, but it's not necessarily uniform because, as Kieran said, you can join nilpotents. So what else I want to say? Yeah.
So then the proof that it's uniform with the Etale condition requires some kind of argument. I mean, it's not
It's
just
requires some small arguments. Essentially, what you're using is that Etaleness is equivalent to the fact that the trace pairing is perfect, and so this means that if you have something bounded, then some of the dual will be open, and then you can make some. And actually, this almost finite Etale business here can be regarded as saying that S circ is almost self-dual under this trace pairing. So let me sketch the proof of 2. So the line of argument is proof 2 and deduce 1 and 3. By proving 1 and 3 in characteristic P. So in characteristic P, 1 and 3 are easy, and so once you know that under tilting finite Etale algebras are preserved, you can get 1 and 3 in general. And so what I want to sketch is the proof of 2. So what you want to do is reduce to the case of perfectoid fields. And so that uses a point. So let X be a point of the X vector for R plus, which gives rise to this completed residue field Kx, and it also gives rise to the residue field of the tilted point, which is a residue field.
So we're just fixing any choice of R plus.
Fix any choice of O plus, yeah. Any R plus. And so these in general will be perfectoid fields. And they are still related under tilting. So the tilt of this perfectoid field here will be this residue field at the tilted point. That follows by using the same result in any rational neighborhood and then passing to some direct limit. And so the crucial lemma is the following, that so I want to prove that finite Etale algebras are the same as finite Etale flat algebras. And I'm trying to do this somehow first locally on the perfectoid space. And so locally around a point, I can somehow look at the category of finite Etale x of u algebras. And then take some of the direct limit of these categories of all x and u. Each of those gives me a finite Etale algebra over this residue field, certainly. But actually, in the direct limit, that's all information there is. So in other words, any finite Etale algebra spreads uniquely over a small neighborhood, which is something that's not true for schemes.
What does the notation say there? Two limit?
Yeah, I mean, direct limit of categories. I mean, technically, I think it's a two limit.
It's essentially expressing this Henselian property of local ring.
Yes, so I wanted to explain this. So let's admit the lemma for a second. So what we then can do is, by the theorem over a field, we know that these are the same as finite Etale algebras over the tilt, which is this residue field at the tilt. And then again, we can spread to a small neighborhood. This means that at least locally or on any point we can we get this equivalence of finite Etale algebras. And what's then left to do is just glue them back together. Okay, and so this reduces us to proving the lemma. And that's actually follows from a very general theorem. There's the following theorem, which in some Noetherian context was proved by Elkig, and then in full generality in this book of Gamma-Ramiro. Interestingly, it's in this book of Gamma-Ramiro on almost mathematics, but it has nothing to do with almost mathematics, this statement. So they're proving lots of interesting theorems in usual commutative algebra. So let's say A is a p-adic, and it's not yet complete, and instead assume it's what's called topologically Henselian in the second book of Gamma-Ramiro. Which means that for a ring of definition, A0 and A, and the pseudo-uniformizer pi, pseudo-uniformizer, that A0 is Henselian along pi. I think this is true for one ring of definition and it's true for all other rings of definition. Then going to the completion doesn't change the finite Etale A algebras, where the functor is either completion or what is the same thing, base extension. And actually, that's a special case of a vastly more general theorem of Gabor, which says that if you have any functor on rings, which has a property that if you have a Henselian pair of a ring and an ideal, then you have the statement that finite Etale algebras of the ring are the same as what the ring mod the ideal. So you assume this property of the functor and it's finally presented. Then also it will have the same output in A and its completion. So you can use this also for K-series mod prime to the characteristic. Also the K-series of A with C mod L coefficients. If L is inverted from A. But I mean,
So what functor do you use for this? The finite isomorphism?
I take the functor which sends A to the category of finite Etale algebras, or the group operator.
Okay.
Should that be A0 star?
No, A star. Yes. Amazingly, it's A star, not A0 star. So you can use this for K-series mod P over Banach QP algebra.
Sorry, in that case, how do you check this property that when you go modern?
I mean, probably we'll discuss this later. No, I mean, it's for... No, I mean, this property is only for rings over... I mean, for Z invert P algebras, you only need this. Well, anyway. Discuss this later. So... So I didn't tell you how to produce a topologically Henselian algebra, but any direct limit, filtered direct limit of complete rings will be Henselian, topologically Henselian. So this implies that if I have AI, a filtered system of complete Tate rings, and I let A infinity be the completion of the direct limit for any topology making this Tate ring. So in other words, I choose any open bounded subrings. Then, well, the category of finite Etale AI algebras is the same thing as finite Etale algebras over the direct limit, algebraically. That's because the finite Etale algebra is something finitely presented, so if something over a direct limit, then the algebra will already be defined over some AI because there are only finitely many generators and relations and so on, and also Etaleness is already defined on some finite level. And then here I can apply the theorem because this is some topologically Henselian algebra, and so this goes isomorphically to finite Etale A infinity algebras.
So Peter,
Yeah?
in the context of this lemma, I mean, of course, one could have imagined just without referring to this Gabor-Romero-Elphick stuff.
You can do this directly. So the Kedai and Leo give a direct proof of this statement, I think, which doesn't use
Well,
This is
we
very
still
general.
need to use the fact that a Henselian ring with finite Etale objects.
Right, I mean, somehow, but you'd imagine, like, yeah, if
Absolutely
you
not.
find an Etale map with adic space is appropriately defined, you have a rational point in the fiber that there should be a section around it, right? This kind of statement is.
Yeah, but doesn't this follow from this?
No, I was thinking, can you prove that sort of thing directly and then use this lemma? But maybe, I mean, you just think it's much harder in the adic setting than in rigid geometry.
I don't know how the work proof in rigid geometry goes. So. I mean, after all, I don't want this just around classical points.
No,
I
I
want these
understand.
very
Yeah,
general
yeah, sure,
points,
sure.
so maybe it's.
Yeah.
Okay.
Although
and-
actually, I mean, in our paper, we really sort of do it around classical points, and that's somehow enough. Because you get these sort of partially proper neighborhoods.
Don't you do it for general Berkovich point?
Yeah, well, Berkovich, sorry, Berkovich.
Okay.
Sorry.
I mean, that's. Yeah.
Yeah, so around Berkovich
I mean, that's
points, maybe,
okay.
I think you can do.
I mean, so
do something like
any
that.
80 point is very close to a Berkovich point, right?
Yeah, and somehow it's enough to do with the Berkovich.
Yeah.
Определенными находят
So this corollary already looks a bit like what we are trying to prove. So we have this two limit of these categories of XU algebras over such a filtered system of algebras. And so we still have to see that we can get this k of x as a completed direct limit. Which, I mean, it's probably a priori surprising that these very big algebras have positive dimension and the completed direct limits, they just give such a small field. So to prove lemma remains k of x completed, and I have to say what the topology is for topology making direct limit of the x plus of u open and bounded. And so, why is that? So this maps to kx plus with dense image. And then there is some kernel. And so we get this completion by afterwards some p-adic competing both sides, in which case this will, well. So the issue is that pi is invertible in I. Why is that? So I probably live in something integral, so it's not clear, right? So if f is an I, such that it goes to 0 here. So if f is an I, then, well, if f is an OX plus of u, such that it lies in I, so it means that the absolute value of f at x less or equal to 1 that f of x is 0, sorry. Then the locus where f of x is at most the absolute value of pi is an open neighborhood of x. Let's call it v. And so then f lies in pi times OX plus of v.
Is that Is it absolute value?
What's the way you write it?
Oh, it's means
I think it's
no,
correct as I wrote, but
I just mean f of x is 0 is an abbreviation for absolute value of x.
yeah. Well, it's equivalent to saying that it maps to 0 in this completed residue field. So this means it's divisible by pi on a smaller opens neighborhood of x, and so this means f is and so this means that if I take this direct limit and complete for the p-adic topology, then this is just so if I invert pi, I get this equality there. And you actually see that this lemma here had nothing to do with the fact that we're working with the perfectoid algebra that works for any Tate ring. So some of the thing is that for in this world of analytic spaces, it's there's not much difference between passing to a restriction at a point and passing to the fiber at this point, because one is just the completion of the other, and completion doesn't change much. So it's very easy to prove base change theorem in Etale. Base change theorems in Etale cohomology. Okay, and so finally I would.
So not from the completion of, taking completion isn't always right exact.
Yeah. Well, if I mod this out by pi to the n for any n, then this goes away, and this becomes an isomorphism.
Well, but completion is not always right exact, so, but I guess it's okay because.
I mean, pi is not a zero. Well, I mean, it's okay.
Unless you need to lift up left condition on the inverse system on the left. Its reductivity is probably okay here because
Yeah.
p-adic topology, not the p-adic topology.
Oh, the transition
is still okay, so.
In transition maps to isomorphism. No, I mean, it's okay. So finally, I would like to define the Etale side. From x to y of perfectoid spaces. It's finite Etale. If for all spar BB plus, which are open in y, say B is perfectoid. The pullback spar BB plus is again some affinoid adic space, it's some spar AA plus. Whereas this morphism of affinoid rings or of Huber pairs is finite Etale in the appropriate sense, and so precise sense is that A is a finite Etale B algebra, which is thus perfectoid itself, and A plus is the integral closure of B plus.
So you finessed that problem in the beginning because of this theorem that you just proved. About the, you bypassed this perfectoid problem earlier.
Yes, but actually I think there is a result in Keplerian view that in general you can glue finite Etale algebras over rational covers even if it's not sheafy, and so the issue shouldn't actually arise. Let me mention this Keplerian view. Same for all fields.
At least if you're over a field. Right, because you do this by some sort of approximation by classical mathematics.
Well, this shouldn't be necessary to assume it's over a field. I mean, I think you can replace your fields by z long series t.
Do you still have the classical, I mean, you need the...
Well, I mean, Huber proves some of these theorems have
okay,
sufficient
you can
generality to do
You
this.
can use that as the base instead. Yeah, so maybe you should be
and some and it's Etale if it's locally a composite of open embeddings and finite Etale maps. So concretely, for all x and x, there exists an open neighborhood U containing x and an V containing f of u, such that we have a diagram. So we have this map U to V, which is a restriction of f to u, and so we require that this is yes. Finite Etale map here, and then an open map here. So there exists a diagram like this. So that's some kind of handicrafted definition, because at least using just perfectoid spaces you can talk about lifting of nilpotents, because perfectoid algebras are reduced. One could try to remedy this by working in some kind of more general category of p-adic spaces. And then check whether this agrees with this one, but I haven't tried to do it. So the good thing about this definition is that if you do the similar definition for rigid spaces, then it recovers the usual notion of Etale morphism. And I guess I'm short on time, so let me just say that Etale covers are, families of Etale maps which are jointly surjective. Families of Etale maps. And let's say that Etale morphisms have all sorts of properties you would like. The compositions of Etale morphisms are Etale. Which is not a priori clear, because like if you compose finite Etale covers and open emergence and on some longer chain, you still need to reduce it to a short chain.
Is there a version of a flat map of
Rational subsets are not flat in general, I think. Yeah, I mean, we are working with non-Euclidean rings, so completion is not flat, and so we're screwed. Pullbacks of Etale morphisms are Etale. And I guess the same with finite.
So like all things aren't necessarily flat.
Yeah. I mean, even open embeddings are not necessarily flat. What else? If you have a diagram like this, F, G, H, where G and H are Etale, then F would be Etale. And also, as is maybe clear from the definition, F is Etale, if and only if the tilde of F is Etale. And so the upshot is that there exists some Etale side X Etale. Which is equivalent to the Etale side of its tilt, just by mapping any perfectoid space which is Etale over to its tilt. And one property that we will need, and that's related to the almost purity theorem, is that if we look at the cohomology of OX plus now as the Etale side, then this is still almost zero. But by the same argument, you can this follows if you prove vanishing for OX. Where you can, sorry, if X certainly. Yeah, there's some kind of Hilbert 90 here. If X and R is perfect. Okay.
So for the little argument you were alluding to for part one, it's the same thing, like if you wanted to show that an Etale map, which is a finite morphism, is finite Etale in this sense, then it would kind of come down to the same kind of.
No, I mean it's also clear that if you have
And if it's a finite morphism, which is Etale, right?
Yeah.
then you would
For
kind of have to
schemes or
localize,
for-
right? No, in this setting.
this.
Right?
Well, I
Then
didn't define what a finite morphism is.
We have notion of finite morphism for adic spaces.
Finite flat. Well, I mean, yeah, but like, okay, but you're in the Noetherian context. I mean, the book is only in the Noetherian world. So,
Oh, under one of those two Noetherian assumptions.
yeah.
Okay, forget it.
So otherwise, I mean, there's no good notion of a general kind of finitely generated Korean. I don't know. Good.